How many people have already studied pre-stressed concrete measure? Everyone? No. Yes, 2, 3. Okay, never mind. So we studied anyway, and we tried to cover some topics so we can connect it to analysis later. Obviously, as with every other topic, we are going to learn something different, something new about pre-stress also, right? And we are going to connect it to the computer-aided analysis and so on, which you may or may not have studied. So, for those of you who have studied pre-stress already, some of this would be basic, others it could be new. First question is always, why pre-stress? Why do we need to pre-stress? Who can answer that question for the people who have studied pre-stressed concrete already? Yes, sir.
So to reduce the deflection?
That's one reason. Another reason? Primary reason. That's not the primary reason.
Reduce in size.
Correct. Because concrete is no good in tension, so we can put pre-compression into the concrete in such a way that when the loading comes, the tension is balanced by the pre-compression which is already present. But then it has many advantages other than that. Okay? And reduce the deflection. Why do you think the deflection is reduced?
Because we have camber. Once the load is applied, it goes straight.
Well, why is there a camber?
Yeah, because the pre-stress it goes up.
Yes. Why does it go up?
Because of the pre-tensioning.
Okay. Concept, you understand the things, but let's see why it really happens and what we can do about this and whether we can make use of that in how many ways. So this is the oldest way, beer barrels, they want to store beer in the barrel and they make it good and it leaks. So to prevent the leakage, they put the straps around it and then tighten it. So it becomes pre-compression. So the wood joints become pre-compressed. So the water leakage is stopped because it has a compressive force which is more than the tension coming from the pressure of the water or beer inside. Okay? So that is how the pre-stressing starts with the metal bags, wooden stairs. So this is the starting point of the concept of pre-stressing, not by engineers but by people who make these barrels. Now the question is, what is different from pre-stress, between pre-stress and reinforced concrete? Many things are different. Number one is materials are very high strength. So you cannot use pre-stressing on low strength materials. It is not worth it. So the pre-stressing materials have to be really high strength, both concrete and steel. Number two, in behavior and performance, less cracking, less deflection, better durability, longer spans, thinner depth, higher loads. All of these good things, right, come together when you pre-stress. In design, we consider new concepts: losses, load balancing, pre-stressing, shrinkage, creep, support settlement, loading sequence. These are all important things because now we are dealing with a completely different concept, not with normal concrete. Because this reinforcement, this steel that you put in is not passive, it is active. Normally when you put reinforcement in a concrete beam, it's a passive steel. It just lies there, waiting for beam to be loaded so it can take tension. Waiting for the concrete to crack so it can take tension. But pre-stressing is active steel. It puts the force into the concrete before the loading comes in, right? So it acts before the loading is coming in, and that creates this loading sequence problem. When to apply the loading and when to apply the pre-stressing, because now you have to do it before the loading comes in. So loading comes in many steps, many ways, in many directions. So then how do you pre-stress it at the right time? So sequencing is very important. In construction, special techniques, special equipment, special procedures and sequence. So it's a technical, highly technical construction. Not everyone can do it. Few people know how to do it well. Very few companies have the capability, both for the design and construction. Normal engineers, structural designers cannot design well in pre-stress. Probably if you're not working for a pre-stress company, you will never be allowed to design a pre-stress concrete member. But if you're working for them, yes, of course you will. And as a designer, you may have to check. But this is a specialized job, and normally it is done by specialized contractors and specialized designers. So in reinforced concrete, concrete and steel bars act together. You already know that. In prestressed concrete, high strength concrete and high strength steel are combined in an active manner. Like I said, they don't act together. They act in an active manner, right? So it's not a passive design, but rather an active approach. So we already said that prestressing is a successful attempt of overcoming concrete's natural weakness in tension. And auto reinforced, so we all know all that. Basically, we convert reinforced concrete, which is we talked about the material types, right? We talked about orthotropic, we talked about isotropic, we talked about anisotropic, right? Normally, reinforced concrete is a highly anisotropic material. It has different properties in all directions. It's a very bad material. But prestressing or post-tensioning, we will call it later, prestressing converts it into kind of an isotropic material. It becomes just like any material, steel or plastic, because the two behavior, tension and compression, which are different for reinforced concrete, are no longer the case. Now compression and tension can be treated in the same way. So it makes your analysis, makes your handling of the material much easier, because now you can deal with it as a isotropic, homogeneous material, rather than a material made up of aggregate and cement and tension and reinforcement. It's kind of disappears, right? So we have these two advantages of prestressing. So we will talk about different concepts in prestressing and how it is done and versus post-tensioning. So let me just come back to this slide later. Let me just see what is basic concept. So like I was saying, we convert the material transform the material into elastic material. Rather than a non-linear inelastic reinforced concrete, we convert that into an elastic material, which makes our analysis and our design assumptions very correct. Because normally in our analysis we assume the materials to be elastic, but I told you that reinforced concrete is not elastic, it's non-linear and it's inelastic. You remember those curves, 4 curves, linear, elastic, linear, and we said reinforced concrete is highly non-linear and inelastic. But prestressed concrete is linear and elastic. So this becomes the simplest material in terms of the behavior after we prestress it. But doing it is not easy. And once you convert that into a linear elastic material, it has a lot of advantages in terms of analysis and design later. First of all, we don't have to worry about crack section properties or cracking, moment of inertia. It's only gross. So gross properties of concrete section can be used for all analysis. Big advantage. Unlike reinforced concrete, where you have gross properties, you have crack properties, you have transformed properties, you have equivalent properties, 4 or 5 types of properties that come in. In prestressed concrete, only one property, gross property, which is great, easier. Linear elastic behavior can be attained. Second is, that is number one, to convert the material, reinforced concrete, into elastic material, which has a big advantage in terms of dealing with the material. To achieve load balancing, second advantage which you may not have studied is to achieve load balancing. That means we do the prestressing in such a way that most of the load is pre-balanced. That means zero stress state can be achieved in a member. When you load it, there is no stress. You can ideally, in a perfect world, you can pre-stress a beam in such a way that after loading, the whole beam has no stress. Zero stress state can be achieved theoretically. So the entire load can be balanced by the pre-stressing action. Imagine a beam having no stress, nothing, no shear, no torsion, no bending, nothing. So all our worries will be gone in that case. Of course, that situation normally cannot be achieved practically, but theoretically, yes. The tendon that we place pre-stressing is actually replaced by load. It is actually a loading on the structure. Unlike the rebar, which is a material, tendon or pre-stressing wire that we place, it's a load, not a reinforcement. It is also a reinforcement at a certain another level, but in operations it is a load. So we actually apply a load in the structure by using a tendon or a wire or a cable. Very small net load remains to be resisted by capacity. So we can almost balance the loading. Of course, 100% balancing not practical, but a lot. Then use high strength reinforced concrete. The first one is advantage at the analysis time, behavior time, within the working range of the structure. Second one is an advantage also in the working range of the structure during the serviceability, during the normal working range. The third one is an advantage at the ultimate strength level. Suppose the loading is overloaded and the effect of pre-stressing is gone, right? After that, the beam becomes a high strength reinforced concrete beam. Suppose the loading is more than pre-stressing and now the pre-stressing effect is no longer usable, then the remaining beam becomes a high strength reinforced concrete beam because we are using the strand which is very high strength, 5-6 times more than reinforced concrete bar. So 1 square centimeter of reinforcement, 1 square centimeter of pre-stress, 5 times more strength here. So the bending moment capacity will be 5 times more that comes free to you, because actually you put it for pre-stressing, but pre-stressing no longer available for any reason or exceeded already. This bar now becomes available to you as a high strength reinforcement. So it's a free ultimate capacity that you achieve from the same process. So you get these 3 very interesting advantages by using the pre-stress. Is everybody clear about this? Good. So, new terms that we need to learn. Number 1, cable, or sometimes called tendons. You know, if you lift your legs here, you will feel your tendons. They're also called tendons, right? These are high strength muscles, very high strength muscles made from many muscle fibers put together to form a tendon that stretches your arm, your muscles. So you have a couple, a ball joint here with the compression, and then you have tendon with the tension. So you have a tension compression couple here, structural engineering. So that tendon is very high strength, extremely high strength muscles made from individual fibers. Same is the case with the tendon here. It is made from individual wires, very small wires. We put them together and to create a tendon out of it. So we make strands and strands made of wires. Many wires put together to make one strand, many strands put together to make a tendon. Ducts are holes, pipes, conduits in the concrete which are placed beforehand in which these tendons pass through to put the post-tensioning or pre-stressing. Okay. Pre-tensioning means wire is stressed before casting concrete. So you stretch the wires, hold them somewhere, pour the concrete, wait for it to harden, then cut the wires. It's called pre-tensioning. Post-tensioning is tendons are stressed after concrete is hardened. So you just place the ducts first, cast the concrete, wait for it to harden, and then you put the tendons through it, put the force, anchor them on the end through dead and live anchors. Okay. And then in that you have the option of bonded or unbonded, internal or external. So pre-tension, post-tension, bonded, external, internal, post-tension, unbonded, internal, external, right? So you have bonded will always be internal normally, and unbonded will be external. So it could be internal or external. So we will talk more about this soon. This is how a tendon looks like. This is the strands coming in. This is one strand. Inside the strand there are many wires. That is a strand, 7-wire strand. So you put 7 wires together, one in the middle, 6 around them. You twist them and it becomes one strand. And then you put many strands together like here and make one cable, one tendon. So then this comes in, this is the anchorage there, that is the anchorage, that is the tendon, sheet, guide, and then lock. So there are many technologies that are used to do this locking, and people have developed patents for that. We will see more about this as we go along. Anchorage, where tendon forces are transferred to concrete. This is the most critical part. You bring a huge force, a tendon through concrete, put some plate on it, and then lock it. That is very critical. How do you lock? A huge amount of force without slipping, right? So there's many patents. Many people have developed designs how to lock so that it doesn't slip. But every anchor has a slip, small slip before it locks, and that some force is lost during that anchorage process, because when you stretch it, when you want to lock it, you release it, it locks it, but it slips a little bit, and that loses some of the force, right, during that slippage. So that is called an anchorage loss. And then prestressing losses. There are many losses that happen. Decrease. This is a decrease in the effective prestress due to immediate losses and long-term losses. Load balancing is a technique or a property of balancing gravity load by forces generated by the prestressing in the indeterminate structure. So load balancing cannot be achieved in a determinate structure. It can only be achieved in an indeterminate structure. Right? We will talk more about this load balancing for prestressing. So these are various terms that you need to be aware of. If something you do not understand, please let me explain it further. Yes. This is the equation that is our only equation actually in prestressing. You know, prestressing is the simplest design. It is just a game of plus and minus, nothing more than that. Plus this, minus that, plus that, minus this. That's it. That's all. It's a very simple calculation. You only have these three things, and you either add them or you subtract them. Three stress components in the cross section. This is the combined stress equation. The first one coming from axial stress, P over A. Second one coming from bending moment and section modulus about one direction. Third one coming from bending moment and section modulus another direction. Right? Two bending moments, one force, and you get the equivalent stress. Why we did not use it in reinforced concrete? We cannot use this equation in reinforced concrete. Why not? Because it's not homogeneous. This is for homogeneous isotropic materials, elastic materials. Concrete is neither. So we couldn't use it. That's why we needed that huge long equation. Right? Now we have this equation. So obviously this equation is much simpler than that. That means prestressed concrete design should be much simpler than reinforced concrete. Right? So let's go ahead and see how it can be used. So basically it is P over A, moment X over section modulus X, moment Y over section modulus Y. So if you can calculate area and section modulus, you are done. That's it. Correct? I wish it was that simple. It never is, right? This is the plot of the stress by using that equation on various sections. This shows you the variation of the stress on various sections if you use that equation. And I gave you the program section builder, right? You can go and try that now. That section builder has ability to put the pre-stressing and check the stresses. And now that will be very useful to you, because you can go back and start checking what I'm saying, and you can see most of these things in that program. And we also need to learn one more thing, that sections may not have only one material. Sections may have more than one material. But as long as the overall cross section is in elastic section, we can use the concept of sometimes you should fill in the gap, sometimes for a change. If we have many materials in a section and the section is in an elastic range, we can use the concept of
Modular ratio.
exactly. We can use the concept of modular ratio to calculate the stresses. That means we can multiply the stress by the modular ratio of that location, and we can get the stress in that material. If it is a single material, modular ratio is 1, so we get the stress, same stress. If it is a steel inside a section, modular ratio of steel is equal to approximately 10, 9, 10, you're right, 10 times modular of elasticity of steel divided by modular of elasticity of concrete is equal to about 10. So you multiply the stress at that location by 10, you get the stress in steel. So same equation that we saw before can still be used even if you have many materials by simply multiplying the stress that you get by the modular ratio of the material at that location, and you can estimate all the stresses everywhere. Correct? So it is still very simple. Now, why would we have two materials in pre-stress? Can anyone think why we would have two materials in pre-stress concrete? We don't need really. And why would we have that? Okay, later to be answered. Think about it. Why would we have, or when would we have two materials in the same section? So then we can put the Ni of that material and get the same stress, okay? So it's still very simple. And now you can get the stresses in composite sections. So you can see from here, stress jumped in the steel section inside concrete because you multiplied the stress at that location by N. So 10 times more stress at the same location as concrete next door, right? But you can still determine this and you can calculate all the stresses everywhere. This is the reason why you will have two materials in a pre-stress concrete. Why? This is a girder, this is a slab. The girder is precast and post-tension, has a high strength concrete. Deck slab is cast in place, has a lower strength concrete. So you may have this variation within two concrete sections in a pre-stress. One high strength concrete, low strength concrete. Low strength concrete, low modulus of elasticity. So N changes, right? So you get the difference in stresses at the, so you can see it's not continuous. It should be continuous, it's not, because different modular ratio. Please read this, all of this. How does prestressing work now? We'll come back to this in a minute. I want to show you some. Okay, already reinforced concrete, the loads are coming, and then what happens? We have reactions, the beam deflects, right, and the neutral axis is formed, and you get tension and compression. All right. So when you apply the load section, which was originally straight, it now comes into tension and compression zone, and this portion cracks or breaks down because concrete may not have the capacity to do that. So this does not exist. In reinforced concrete, this does not exist. It cannot exist because there is no concrete there. So that whole section that you started with is gone. So you cannot determine this from this equation anywhere. So, but you still can sum up the tension and the compression at the bottom. If you can replace the entire tension by steel, this can still work, right? So all of the tension, calculate and replace it by steel, and this one by concrete, you can provide the capacity through this couple. Now we talk about the pre-stressed beam. We take a beam and at the bottom, at this location, we put some force. Doesn't matter where the force is coming from. Just say that we put some force on the beam, right? So what will happen when you put this force on the beam? What do you think? Two things will happen. The beam will shorten and it will also bend up, right? Because, so the beam will go like that, okay? And because of that, if you now apply the loads, if you handle everything, it will become straight again, correct? So which means that there will be no stress anymore because you started with a straight beam with no stress. Put pre-stressing, it went up, you applied the load, it came down, back to the neutral position, no stress. And that is the ideal situation. Of course, we cannot achieve it in reality, but we could in lab do that. This is how the stresses will now look like. Let's look at it in the stress direction. You can see from here, if you apply the load on a normal beam, the bending moment diagram will look like this, correct? And then the stresses at the middle section will look like that, tension and compression, correct? We have seen that from the previous diagram. And they will be calculated by using that equation because there is no my, there is no p, so we can calculate the stress by simple F is equal to mx over something like that, correct? And no problem? So that's fine. Now let's see, you take another beam, another case, and you put the force right in the center of the beam, not bottom, not just in the center, and you apply P. So you will have compression. So this is constant compression will be created at the section in the middle, correct? Now if you put them together, and this will be calculated by F is equal to PA, and the stress will look like this, correct? Now if you put them together, what will happen? We put that one and P together, sum them together, then you will get this situation. You will get the stress from the bending moment plus the stress from the axial force, and the stress diagram may become like this depending upon the force. That means you may actually have no tension, all compression or zero tension depending upon how much force, how much moment. This is just a theoretical, but basically the idea is that you use this to add this one, P over A plus mx, so one more component comes in, and plus minus depending upon how the signs are converted, you could have a situation like that. And that is the whole idea, addition of stresses coming from loading and the pre-stressing. So this is the case where you put the load right in the middle, center of the section, which actually is not a very good way to go, right? It is not a very efficient way to go. So there is no load balancing, there is no negative bending, no upward, nothing. Just pure compression, balancing the stresses, right? Next case. Same, but this time we put the load at the bottom, eccentricity EY. Because of the load is here, a net bending moment, constant bending moment will be generated on the section upward, correct? Equal to P into EY, negative, because this is negative direction, Y is negative. So negative bending moment will be generated, which will be then balanced by the positive bending moment, and this one, this equation is used, and we will get now this one, reduced tension or no tension depending upon what we do here, correct? Because this will be a reverse diagram of that, and then you add this one, you will get so that with that. So this is the bending moment diagram, This is the pre-stressing diagram, and this one, combine this one, you may get something like this, plus MPY plus MX. So now we have three components coming here. One from the load, one coming from the force, one coming from the bending moment because of the force, which is because of the eccentricity. So important thing is eccentricity of the force from the centroid. If there is no eccentricity, no bending moment due to force. But if the force is eccentric, the bending moment will be generated and you will have another component. So you get the benefit twice. One from here, one from the pre-stressing moment, and you get two benefits from that if you put it correctly. Now what's wrong in this picture? What is wrong is that at the end this moment is constant, but the loading moment is becoming zero. So at the end of the beam,
The movement should be 0.
we will have net moment causing tension because it is not being balanced by the axial the downward moment. So the pre-stressing is actually causing a moment, net moment at the end, which is going to cause tension, and that is not good because you still have tension in part of the beam. Correct? Because this is a constant moment. So at the end, the diagram will only be this one, not balanced by that one. And the balancing is not matching with the bending moment. Somewhere it is being balanced, somewhere not. Because the bending moment diagram from the actual load is like this, and from the pre-stressing is constant. So they don't match well. Some location, yes, they might match, but other location they will never match. So you cannot create a zero stress state in the beam at odd locations. You can only create it at one location. And the beam may not fail at the middle, it may fail at the ends because you still have tension there. Are you clear? Right? So that means putting the strand in the middle was okay, but it was not so good because we were not balancing we were not getting any benefit from the moment, only axial load. We move it down, but the problem is if we move it down, we get the benefit in the middle, we don't get the benefit in the ends. So what do? We change we say let's balance the moment from the pre-stressing to be of the same shape as the moment from the applied load. So they cancel each other everywhere. So we need to create the bending moment from the pre-stressing of the same pattern as the bending moment from the load, so that when we put them together, they cancel everywhere. So which means we put this strand like that with their not constant P, but E changing in the same proportion as the bending moment is changing from the load. And then the P can be adjusted to match the value.
Of the applied loading?
Sorry?
Of the applied loading?
Of the applied loading. So applied loading is, let's say, something X. Creating a moment, and it's a parabolic shape. Bending moment diagram is a parabola, you know that, right? So if the tendon profile is also parabola, that means the moment created by the tendon will also have a parabolic shape. And the value is simply a multiplication P multiplied by that ordinate. So we can calculate the P required to balance the load moment in the middle, and it will be balanced everywhere because both have the same profile. Clear? So finally what we learned so far is that the tendon profile must match with the load moment profile. If you can match the profile of the tendon with the shape of the bending moment, then you can perfectly create a beam with zero stress state, not otherwise. Clear? Now here's the problem. This beam may have 1 point load, 2 point load, some UDL. Some are live load, some are dead load. How do you balance them with a single tendon profile? Because you have to put the tendon there beforehand. but the loads are of different, creating different bending moments at different load combination. And what about earthquake? So, which basically means we can never balance all the loads, because one tendon profile can only balance one load condition, not more than one. Correct? So that is why pre-stressing can never be 100% stress-free, because some load condition, some load case will always be not matching with the original pattern. Second issue is the load UDL is never there all the time. For example, this room is empty, no live load. So if you put the pre-stressing to balance the live load, that means when there is no live load, you will have an upward extra moment causing tension. When live load comes, it will balance. When you go out, it will come back again. So that's not good, right? Which means, finally, the conclusion is that you can only balance the dead loads by the pre-stressing. You normally cannot balance or should not balance the live loads, because they come and go, and when they are not there, pre-stressing may cause tension at that time, because it will exceed the bending moment from that load at that time. So normally the dead loads are UDL, and normally they are parabolic configuration of the bending moment. So final conclusion is that we can put a parabolic tendon in a beam and apply the force in such a way that it balances about 80% of the live load. Why not 100%? We are not sure about the load, number one, but more importantly, creep. A little bit unbalanced may cause creep and then the beam may go upwards. In many places you might see that instead of downward deflection, you actually have upward deflection, because over pre-stressing. Somebody was too good, they put the pre-stressing, try to balance 100% of the load, and the load isn't there, right? So it goes upwards. So that's why normally what we try to do is we try to put a tendon profile which is parabolic, and we put the force in such a way that it balances about 80% of the dead load. And the remaining live load and dead load, what happens to them then? Sorry? Two things. We allow a little bit tension, because concrete can take some tension, and we put some reinforcement to take care of that extra remaining load, which is very small, which leads us to partially pre-stressed beams. That means we have pre-stressing, we have also reinforcement, they act together. Most of the dead load balanced by pre-stressing, remaining dead load and live load taken care of by normal reinforcement. So it is a combination of pre-stressed and reinforced concrete that finally is our solution. And normally in bridges of this span that we are talking about, the dead load is the predominant, live load is rather small. You will be surprised that 90% of the bridges are designed for dead load. Anything longer than 45 meters, live load becomes too small. We don't even care about it. Longer bridges like cable stayed and big, live load is just nothing. It's almost nothing. The self weight is the main thing. So bridges are mostly carrying self weight. Live load is a very small thing that we just get it in as a freebie. So now this is the summary of whatever we have been talking about. This way in the middle of so we can convert that into equivalent moment and all of that stuff that I showed you. So ultimately, what do we have? We have plus minus. It is nothing but a plus minus game of the pre-stress behavior, and this diagrams tell you no prestressing, no external force, just prior to cracking, just prior to failure, different conditions of the stress diagram on that one, strain, stress, and then stress resultant. So this gives you a complete picture of the beam behavior in various stress states, right? So it gives you a summary of what is happening inside a pre-stress and normally reinforced concrete beam. So you can study a little bit more. Basically, it's just explaining what we have already seen. Now, the loads coming due to pre-stress. So far, we have only talked about the eccentricity of the force and moment due to eccentricity. But we did not talk about the inclination of the force that is pulling something, like the cable effect. Suppose there was no beam in that location and still you hang a certain cable, right, with a certain profile. So that cable has a capacity to carry the loading because of its geometry, right, because it has inclined forces and the tension there. That cable effect, if you put the cable straight, it has no capacity to carry load, correct? If you just put the cable straight, you cannot put load on it. But if the cable is hanging, you can hang some load on it because of the geometry of the cable, because of the angle of the line here, because of the resultant, this V component, right? So because of this V component, we get extra force that is coming up, not only the bending moment because of the eccentricity, but also this V component, which will give you a net resultant force at the end also. So, which means that this cable is not only a pre-stressing inside the beam, it is also a member with an incline, with the force which is inclined, having a resultant horizontal and vertical. Horizontal component puts pre-stressing, vertical components create a vertical force onto the beam. So that concept, I'll just go from here rather than going into the display mode. Is this okay for you? Okay. So that concept creates this secondary load effect on the beam. That means when you put the cable like this one, it creates a loading on the beam, just like as I mentioned to you, you hang a cable there and you try to pull it. It will try to straighten up and it will lift something up. It has nothing to do with the force and moment eccentricity. It is the geometry of the cable which is trying to straighten and lifting the things up. And that is called the vertical force will be applied upwards, and that cable trying to lift down will create a loading on the structure. These are called secondary loads, right? But in a simple beam, that cannot happen because there is no way for this vertical reaction to be balanced because all you are applying is horizontal load. So vertical reaction cannot come on the supports. So load cannot be balanced. Do you understand the point? Just like I showed you yesterday. If you have a truss, if you apply a load, the horizontal reaction cannot generate if there is one side is a roller because there is nothing balanced. Same is the case here. If you are applying a horizontal force, vertical reactions cannot exist because equilibrium will not be attained. Do you understand the point? But here, the vertical reactions can exist because some reactions will become positive, some will become negative, and the net will still be zero, but there will be reactions up and down, and there will be loading generated up and down. Because there are more than two supports, so one of the supports or two of the supports can develop upward reaction, other two can develop downward reactions, net vertical reaction still zero, but there is some reaction now developed, so some forces will be developed on the beam internally. So that's why we call them hyperstatic or internal or secondary loads, that they are generated within the structure because of the indeterminacy. So that means we are saying that vertical forces are generated in the structure because of horizontal forces. right, in a beam, which normally should not happen. But here it is happening because the tendon is curved and it is trying to straighten out. So it pushes some supports down, it pulls some supports up. Internally, a completely internal self-contained loading is generated, which is balanced but causing bending moment on the structure. Now this is a very fine line. Many engineers do not seem to understand that these are two different things. Eccentricity of the force causing bending moment and the profile of the tendon causing forces which cause moment and reactions are two different things. Alright? So if you are clear about that, my job is done, we can stop now. Okay, so this is the key to the pre-stress or post-tensioning of the indeterminate structure, continuous beam, slabs, continuous girders, because we get double benefit. We get benefit from the pre-stressing, we also get benefit from the balancing of the load, physical balancing of the load by lifting of the beam, not just the balancing effect because of the moment created by eccentricity. So which means we can replace now the tendon, we can take it out and replace by this loading, and that's it. We can analyze the structure. So tendon, which was supposed to be a reinforcement, now becomes a load on the structure. So to analyze the structure, you need to convert the tendon into loads and apply the loads, and once you have applied the loads, then you don't need to consider anything. The stresses that you get from the analysis are already the final results for you, because it includes the effect of the bending moments from the pre-stressing, it includes the effect of the actual loading, it includes the axial forces, and then you can directly use the final results to check the stresses using the stress equation, and you are done. So the design is no longer needed. It is only now a stress check, because the pre-stressing is converted into a load, and load cases which can be combined. Now the advantage of this thing is that you can combine this with many different ways in many sequences, right? You can combine so this loading is one loading, you keep it separately. Then you bring live load, then you bring dead load, then you bring earthquake load. You bring whatever loads you like, and you just combine them the way you want them, based on the sequence of the loading. Loading come first, pre-stressing come later, pre-stressing come first, loading come later, live load with this, not. So you can do it, it's just now a combination game, right? And then degree of pre-stressing. This is a summation of what we have been talking about. Unreinforced concrete, no reinforcement to resist tension. So concrete can simply crack and go away, we don't care. Now you might say, oh, but we care. Give me an example of unreinforced concrete. No, structural, unreinforced concrete. Pavements, road pavements, dams, most of them are unreinforced, right? Because we utilize the tension and go up to that point. So it is not completely a waste. All road pavements are mostly unreinforced. Reinforced concrete, steel bars as reinforcement to resist tension. Partially pre-stressed concrete, high strength steel, pre-tension to reduce tension, steel bars as reinforcement to resist tension. So this is to reduce tension, this is to resist balance tension. Fully pre-stressed concrete, high strength steel, pre-tension to reduce tension, nothing left to. So if there is tension, bye-bye, right? But we allow some form of tension here. And because we are using very high strength concrete, so that allowable tension is quite high actually, it's not so small. Because pre-stress we normally use high strength concrete. And FC, as you know, the tension capacity is related to the square root of the compression capacity, correct? So we still get quite a substantial tension capacity that we can utilize. Pre-stress stages. There are many stages in pre-stressing, and this is the last slide. We're going to stop here. Initial stage, intermediate stage, and final stage. Because loading is coming in different manners also. So you need to create the pre-stressing and consider many, and this is basically the complication in the pre-stressing stages. Because you have to think about all the stages the structure is going to go through. When I'm pre-stressing, is the dead load there or not there? Right? Can I pre-stress all of it now? Can I leave some now? So we do stage pre-stressing. For example, the girder is only there, the slab isn't there, you do some partial pre-stressing. Then you put the slab, you do more pre-stressing. You put some more flooring, you come and do more pre-stressing. Because if you pre-stress everything in the beginning and the slab load is not coming, you will break the girder. So pre-stressing stages are very important. Before pre-stressing, during pre-stressing, at transfer, during transport, final stage, sustained loading, working load, cracking load, ultimate load. Right? So I'm going to stop here because we have now many concepts that we have introduced today. Alright, so pre-stressing is a very good idea. It's very simple in principle, very difficult in application because of all these complications plus the site, and it's very critical because you don't want to pre-tension, post-tension and break something before it is even utilized. The most complicated example of pre-stressing or post-tensioning operation is balanced cantilever construction, balanced cantilever bridge construction. Do you know what that is? Anybody who knows about that, raise hands. Balanced cantilever bridge construction. Okay, we will talk about that. Just to give you an example, what a really complex post-tensioning operation can be. One of the most complex is application of pre-stressed concrete is, in practice, is balanced cantilever bridge construction. Alright? So I'll give you next time when we meet.